Hello, Accelerated Chemistry students. This is Ms. Christopher, and this is your Chapter 21, Section 3 video notes all over electrolytic cells. So let's talk about electrolytic versus voltaic cells. The process in which electrical energy is used to bring about a chemical change is called electrolysis. You are already familiar with some of the results of electrolysis, such as gold plating jewelry, chrome-plated automobile parts, or silver-plated dishes. The apparatus in which electrolysis is carried out is an electrolytic cell. An electrolytic cell is an electrochemical cell used to cause a chemical change through the application of electrical energy. An electrolytic cell uses electrical energy or a direct current to make a non-spontaneous redox reaction proceed to completion. So if we were to look at the difference between the two, if we were going to look at voltaic versus electrolytic, electrolytics basically have a battery. They're the same thing as a voltaic cell. They don't have a salt bridge, and they do have a battery. So in both voltaic and electrolytic cells, electrons flow from the anode to the cathode in an external circuit. The key difference between voltaic and electrolytic cells is that the voltaic cells, the flow of electron is a result of a spontaneous redox reaction, whereas in an electrolytic cell, electrons are caused to flow by an outside power source, such as a battery. In voltaic cells, the anode is the negative electrode and the cathode is the positive electrode. And in electrolytic cell, the cathode is considered to be the negative electrode. Electrolysis of a solution or of a melted or molten ionic compound can result in the separation of elements from compounds. Electrolytic cells are also commonly used in plating, purifying, and refining metals. Let's talk about the electrolysis of water. When current is applied to two electrodes immersed in pure water, nothing happens. When an electrolyte such as sulfuric acid or potassium nitrate in low concentration is added to the pure water, the solution conducts an electric current and electrolysis occurs. When an electric current is passed through water, the water decomposes into oxygen gas and hydrogen gas. Water is oxidized at the anode via the following equation, and water is reduced to hydrogen at the cathode, following this equation. The overall cell reaction is obtained by adding the half reactions after doubling the reaction half reactions to balance for the electrons. So we've done this numerous times. So we're just going to add our two half reactions together to get the overall electrolysis or decomposition of water. The ions produced tend to recombine to form water. So we have 4 H pluses and 4 OH minuses will come together to make 6 waters. Therefore, the net reaction can be written as follows. We have 2 water molecules that will split into 2 hydrogens and 1 oxygen. So now let's talk about the electrolysis of brine. And if the electrolyte in the aqueous solution is more easily oxidized or reduced than water, then the products of electrolysis will be substances other than hydrogen and oxygen. An example of the electrolysis of brine, a concentrated aqueous solution of sodium chloride. This process simultaneously produces 3 important industrial chemicals: chlorine gas, hydrogen gas, and sodium hydroxide. So chloride ions are oxidized to produce chlorine gas at the anode. Water is reduced to produce hydrogen gas at the cathode. And sodium ions are not reduced to sodium metal because water molecules are more easily reduced than are sodium ions. The reduction of water also produces hydroxide ions. The electrolyte in solution becomes sodium hydroxide. The half reactions for this are as follows. We have chlorine as an ion going to chlorine gas, and we have the reduction of water going to hydrogen gas and hydroxide ions. The overall ionic equation is the sum of the 2 half reactions. So here's our oxidation, here's our reduction. When we add them together, we get the following equation. The spectator ion, Na+, can be included in the equation to show the formation of sodium hydroxide during the electrolytic process. So if we put in where we had our Cl minus on the left and our OH minus on the right. If we have our Na in there, you can see that we make sodium chloride with water to produce chlorine gas, hydrogen gas, and sodium hydroxide. Now let's talk about the electrolysis of molten sodium chloride. Sodium and chlorine are produced through the electrolysis of pure molten sodium chloride rather than an aqueous solution of sodium chloride. Chlorine gas is produced at the anode. Molten sodium is collected at the cathode. So here are our two half reactions. And when we add those two half reactions together, we can see that we have sodium chloride as a liquid making pure sodium and chlorine gas. The electrolytic cell in which this commercial process is carried out is called the down cell. The cell operates at a temperature of 801 degrees Celsius, so the sodium chloride maintained the molten state. Electrolysis has many important applications in the field of metallurgy. Many of the shiny metallic objects you see every day, such as chrome-plated fixtures, nickel-plated coins, were manufactured with the help of electrolytic processes. Electroplating is the deposition of a thin layer of metal on an object in an electrolytic cell. An object that is to be silver-plated is made at the cathode in an electrolytic cell. The anode is the metallic silver that is used to be deposited. The electrolyte in a solution of silver salt, such as silver cyanide. When the direct current is applied, silver ions move from the anode to the object to be plated. Electroforming is the process in which an object is reproduced by making a metal mold of that at the cathode of a cell. A mold is an object that can be coated with metal so that it conducts a current. And then it is electroplated with a thick coating of metal. Electroforming is used to make jewelry and tubing for chemical instrumentation. In a process called electrotrowning, impure metals can be purified in electrolytic cells. The cations of molten salts or aqueous solutions are reduced at the cathode to give very pure metals. A common use of electrowining is in the extraction of aluminum from its ore, bauxite. Bauxite is impure alumina. It is a Hult-Héroult process. Purified alumina is dissolved into molten cryolite and heated above 1,000 degrees in a carbon-lined tank. The carbon lining connected to a direct current serves as the cathode. The anode consists of carbon rods dipped into the tank. At the cathode, aluminum plus 3 ions are reduced, forming molten aluminum, and at the cathode, carbon is oxidized, forming carbon dioxide gas. The overall reaction is as follows. In the process of electrorefining, a piece of impure metal is made at the anode of the cell. It is oxidized to the cation and then reduced to the pure metal at the cathode. This technique is used to obtain ultra-pure silver, lead, and copper. Other electrolytic processes are centered on the anode rather than the cathode. Electropolishing, which is when the surface of an object at the anode is dissolved selectively to give it a high polish. In electromachining, a piece of metal at the anode is partially dissolved until the remaining portion is an exact copy of the object at the cathode. And that is the end of your Chapter 21, Section 3 video notes. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbook resources CD and pearsonchem.com. Thank you so much. Have a good night.